Hello, everyone. Let me begin with thanking the organizers, and let me join you, the Amida, in thanking the audience, because not only it's a Sunday morning, but happens to be February 14. So this work was done in collaboration with Arndt and Roland, who are there in Dresden, Steve and Pullman, and Arul is second. So essentially, this picture itself kind of is the full talk. I am interested in the bipartite system, whose individual subsystems happen to be completely chaotic. And what I am going to see is that if I turn on the interaction between them, how the properties, which I will characterize in terms of spectral fluctuation, are going to vary. In that order, I will basically say something about universality and all. Motivation for this kind of studies are multifold. Let me begin with the random matrix perspective. So we know that if I have a single system, and if it's classically integrable, then the spectral distribution fluctuation would be of exponential type, Poisson type. If it is chaotic, then I will have one of the level repulsion, depending on whether time reversal symmetry is broken or not. What happens if I couple these two systems? So if I mean, we are interested in multipartite, but let's begin with the bipartite system. This can be realized in chaotic quantum dots if I put two particles and then drive them. Non-integrable spin chains. So the question are that, we will see in due course that if they are non-interacting, even though they are chaotic, we'll see something like Poisson kind of structure. And if they are coupled very tightly, then they lose their identity and again behave like one system. And again, you expect because they are chaotic, so RMP. But what happens in between? That's the transition, and that's what I am going to characterize here. And then there's a huge motivation from quantum information point of view to characterize the entanglement generation, and that will be discussed in the following talk. So this is the mathematical object that I will be dealing with. So basically, I will be dealing with the unitary operators and interaction, and this eigenvalue equation, the quasi-energies, that's what I am interested in. We'll do the statistics. Let me introduce the system, the subsystem, which is a standard map, basically a kicked rotor. So a particle is moving on a circle, and I am kicking periodically, right? Since I have the Hamiltonian, I can write immediately its equation of motion, can do the stroboscopic analysis, and map after each kick, and details can be seen in paper by Chirikov. Quantum mechanics is sort of equally good, at least at the level of equation of motion and all. One can do this integrals. One can integrate these things for one period, thanks to this presence of delta functions and all. And one can write this unitary operator in terms of the P square and potential. And the details can be seen in a nice review by Israeliev. So let me couple them. So I have let me mention one more thing, that there's a parameter K here, which is like the strength of the kicking. So if I put K equal to 0, then it's very simple that it is integrable. And if I introduce any non-zero value of K, it becomes non-integrable. If I hit it too hard, it will become chaotic. Okay. If there are integrable regions, it would be of measure 0, so I will happily leave them out. So I am choosing my subsystem, so one 2D coupled system, and choosing the parameter as 9. You can see the phase space completely chaotic. Another 2D, which I have chosen as K2 as 10, pretty much the same. And then I make them interact by a potential which is like cosine of the sum of the position of P. If I have non-zero and then b equal to 1, so essentially if I mean classically if you see then the phase space, I mean I don't have the picture here, but it's same more or less. But we will see what happens in quantum mechanics. Let me introduce the spectral fluctuation, I mean, so level spacing distribution, by which I mean that, so I am doing here for the unitary map, so I am interested in the quasi-energies, and then I will take the difference, nearest neighbor. Normalize it by mean spacing. Normalization is sort of necessary. And then if it is a regular system or integrable system, I expect it to be Poisson-like, right? And then for a circular billiard, which is nothing but a particle moving in a circular enclosure, you can have your equation of motion, I mean, constant of motion. It is an integrable, well-known system, we get the exponential. I take the standard map, drive it at k equal to 10, have shown already the phase space, which is completely chaotic. And then very nice S square dependence can be seen, the level repulsion. So that's the RMT. Let me see now what happens in the bipartite. So I had two systems. I just took, I'm looking at as a part of subsystem basically. So it's a full system. I took U1 tensor U2, that's the object right now because interaction is 0. And I get a nice exponential, even though the subsystems are completely chaotic and all. This fact has been mathematically proven in the paper not long ago by Tchaikovsky and group that this is something which one can expect. And this can be intuitively also reasoned out because all the correlation is in one system. So if I take, say, electrons, they know that I have to repel each other. If I take positrons, they know I have to repel each other. But if I mix electron and positron, then there is nothing to prevent them. So they can come as close as possible. And that would sort of push all the zero, I mean, basically give all the zero spacing sort of. It's quantum. Okay. So, so here basically is, so this is quantum. So I have unitary operator. And the object that I was talking about is here. So each unitary operator and the U1, 2. So between two planes. Yeah, right. That's the flow K, yeah. Okay. And then this can be understood nice. Yeah. Yeah, I mean, so that was kind of an, I mean, that's not a correct analogy, but what I was trying to say that what was this depletion here at near spacing 0, this can be I mean, this can be nicely put key that it will go out. Yeah, no, I mean, so if I take only charged particle into the picture, they would like to come as close as possible. So 0 is the maximum. No, it's just because of normalization, it's a normalized distribution. So the maximum probability will go to. But anyway, it was just an analogy, so cannot be taken very seriously. Okay, so strongly interacting system. I have now the same K1, K2 as 9.8 and 10, and I now drive coupling is like B equal to 1. So it's a nice RMT. So that's the. Now, what do we expect? I mean, I have this unitary operator and it's a finite dimensional matrix. So n is 1. I noted in the second slide, I guess, that the Hilbert space dimension is 1 parameter. And the second is coupling. So there are 2 parameters. And if I vary, then from Poisson, they will go all the way to this RMT. by varying any of this. So basically, is there a parameter which kind of connects this n and b? Or what is that parameter with respect to which we should study the transition? If at all it exists, so this picture shows that, yes, there is. So I have 3 different values, b, n, b 0.02500, and 0.0150, and 0.0425. And it shows that they nicely come on each other. So it turns out that this is the parameter. So this combination of n and b basically collapse all these things on one single curve. So the aim is that how to reason out that this is the correct transition parameter, and if at all, can we find out the distribution. To understand these things, we introduced a RMT ensemble, which is motivated by this dynamical system. So unitary operators, CUE, and then coupling. I am taking the coupling as a diagonal matrix, which is distributed uniformly. Then it turns out that there was this kind of studies in late 80s where GOE to GUE transition was being looked at. And then there was a whole perturbation theory where the transition parameter comes out to be the mean square of the diagonal matrix element divided by the mean level spacing. So here in our case, for RMT ensemble, we will get n square epsilon square, and for coupled map, we will get this. As I said that this is a model for this dynamical system, we can relate them, and this epsilon turns out to be n. So this factor comes out automatically by doing this calculation perturbation theory, but all is important. I mean, n square b, if I take, that itself is sufficient, because anything constant is after that you multiply by another constant, doesn't matter. Well, the reason was this, that, so I mean, just an idea that how one can do this kind of thing. So I took this, I evaluated this b square in the diagonal basis of U1 tensor U2, and it nicely comes out this expression, which if I take the small epsilon limit, I will get n squared. Okay, so, and if I do a perturbation theory again, it will give me an ugly looking expression for probability distribution function of nearest neighbor spacing, but works beautifully well. And one can scan the whole transition in terms of the variance of spacing. Looks really nice. And let me summarize at this point by saying that there was this introduction of RMT ensemble, in which, through which we can identify that what is the universal transition parameter, and then we can find out the spacing distribution as well. And the perturbation theory works amazingly well in whole range. The details can be found in this paper, and thanks for your attention.
Any questions?
Okay, I can be loud. What happens if the kicking periods in the two coupled systems are not equal, commensurate or incommensurate?
Yeah. So, yeah. So, yeah. So the Hamiltonian, if you have, then you have the same thing. But I mean, there could be a variant of these things if I change the, I mean, if I K1, K2, and other values, and if I take a different kind of interaction, there I can say that it doesn't matter.
For what period you choose for picking them, and so if they are, they may or may not be equal.
Yeah.
It's, yeah.
So just purely in terms of the strength of these two systems, the perturbation is weaker than these two individual standard maps. Is that why your perturbation theory works very well?
Actually, B equal to point, I mean, okay, so lambda, since I am characterizing everything in terms of lambda equal to 0.2 itself is very large, but it works. So, so if I, yeah, here. So it's maybe 0.3 and all, and you will already go to this limit distribution, which is CV.
So I'll thank the speaker again and invite the next one.